Okay, so hello everyone, and thank you for being here and for inviting me. I'm very happy to do this talk. Okay, so this is a kind of a survey talk on the topic. So the goal today is to relate the more algebraic properties of fields and the Diophantine properties of fields in the sense of studying rational points and varieties over fields. Okay? And so to start with, I'm going to start with the Diophantine side. The starting point is well, theory that was developed in the first half of the 20th century by people like Cité, Arteche, and Lang. So they defined the following. So the idea is, if you work over a field and you take an equation in lots of variables and of low degree, it should have quite easily solutions. Okay? So more precisely, the definition is the following. So you take K a field, and you take I a non-negative integer, and you say that K is Ci if whenever you take X in Pnk, this is a projected hypersurface of degree d, and with the inequality d to the I is smaller or equal than n. So this is the inequality that tells you that the degree is low and the number of variables is large. Okay. Well, then X automatically has a rational premise. All right. So let's see some examples to understand how this notion behaves. Examples. The first example is a small, very easy exercise. So what does it mean for a field to be C0? Well, the field is C0 if and only if it is algebraically closed. Okay? So these are, in some sense, the simplest fields from an arithmetic perspective. More interesting example is the case of finite fields. So this is maybe a theorem you've already seen. It's called the Chevalier-Warning theorem. Chevalier-Warning, which states that finite fields are C1. Okay? So if you take an equation in more variables than the degree, homogeneous equation in more variables than the degree over a finite field, it will always have a non-trivial solution. Okay? Third example is a transition theorem. So this is the theorem of Cité-Lang-Nagata. So what happens if you move from a field to, let's say, a finitely generated field or a finite transcendence degree extension? So take large K over little k of transcendence degree, let's say delta, and if little k is Ci, well then large K is Ci plus delta. Okay, and so it's because of this transition theorem that the definition takes this inequality, or this inequality that goes well when you look at this transition theorem. Works well. Okay, and maybe last example I would like to mention. Of course, there are others, but last example. So this is the theorem of Greenberg, which is also a transition theorem, this time for Laurent series fields. So if K is Ci, then the field of Laurent series in one variable over here in K is Ci plus 1. Okay. And surprisingly, I mean, it's quite a funny situation in number theory here, that this is in some way the local version of this one, and in fact, this is harder than this one. Essentially, you first prove this one, and from this one you can deduce this one, and that's not easy to do, but that's how it works. Okay, so let's say these are positive results of Ci fields. Of course, there are fields that are not Ci. Okay, so counterexamples. Well, there's a counterexample you all know. You just take K to be a subfield of the real numbers. Well, it's not Ci. Whatever the I, okay, just because you take a sum of square and it's always positive. Okay. A more interesting counterexample is the case of p-adic fields. So take QP. Well, our team conjectured that QP would have the C2 property, and he got it wrong. So it's not C2. It was seen by Bergenian. And later on, in fact, it's not CI, what's IPI. So this is a archetype of Karatsuba and Ballet. Okay, so that's mainly what he wanted to say about these CI fields. Now, I told you at the beginning of the talk that the goal is to relate Diophantine properties to more algebraic properties. So the algebraic properties, I'm going to encode them in terms of the cohomology of the field. Okay? So when you have a K field, you always have a cohomological theory that is associated to it. So it's what people call the Galois cohomology. Okay, and
Can I do something?
sure.
So you're not allowing the hypersurface to be the power of a smaller degree hypersurface, like non-reduced.
Oh, it could be non-reduced. Yes.
But then how come like?
But you have this inequality anyway.
Okay, yes, that's all right.
Okay, we see it. You have K field, and then you have the Galois cohomology. So this is usually denoted Hn of Km. So for those who were in the talk yesterday, I'm repeating a bit myself, but for the others, I'm going to briefly say what this is. So this is an abelian group, okay? And well,
Okay.
yes.
Okay. So then maybe not being C2 implies not being twice S, so C2i. Right? Like if you have a so there exists a polynomial of some degree such that of some degree b squared less than or equal to 12 that doesn't have any rational points. No power of that polynomial would have rational points, right? So
Sure, but I mean the degree increases in that case. So if you want C2i,
Yes.
it goes the other way around.
Yes.
So here the n is the degree of the cohomology, so it's a non-negative integer, and m is the coefficient, so it's what people call a Galois module. Okay, and so it's an abelian group together with an action of the absolute Galois group of K, so Galois K sub over K. K sub is the separable closure. And this action has to be compatible with the abelian group structure, and it should be continuous. Okay, so this is a non-trivial condition because the absolute Galois group has a topology. It's not discrete. But okay, so of course I'm not going to define these groups in general, but just to show you a bit what kind of information they encode, for you to see that they encode important algebraic information on the fields. Let me show you some examples. So the first one, you can look at H1 of K with values in Q mod Z. So here Q mod Z is the abelian group Q mod Z with the trivial action. Okay. Well, this is the continuous homomorphisms that go from the absolute Galois group to Q mod Z. Okay. So if you prefer, it's the character module of the absolute Galois group. So it encodes a lot of important information on the Galois group. Second example, you can look at H1 of K with values in mu n. So here n is not divisible by the characteristic. And mu n is the group of n roots of unity in the separable closure. So since the absolute Galois group acts on the separable closure, it also acts on mu n. Okay. And so this is the Galois module. And its H1 encodes information on the multiplicative structure of the field. So this is K star modulo nth powers. And maybe finally, last example I'm mentioning today. So one can look at the H2 of K with values in K sub star. Okay, so again, the absolute Galois acts on K sub, so it acts on K sub star. And this H2 is what people call the Brar group of K. So it's simply BR of K. Brar group. Okay, and it's an important group because if you have an algebraic perspective, it classifies central simple algebras over K. These are finite dimensional algebras, non-commutative in general, whose center is K itself, and simple means that two-sided ideals are everything or nothing. So from an algebraic perspective, it classifies that, and from a geometric perspective, it classifies several Brar varieties. Over K, which are varieties X, such that when you go to the C-parallel closure, they become isomorphic to some projective space. Okay. For instance, in dimension 1, those are conics. All right, so I hope this shows you a little bit what kind of information the Galois cohomology can contain. And so today I'm interested in an invariant of the Galois cohomology, which measures its complexity and which is called the cohomological dimension. The cohomological dimension of K. All right, so I'm going to define it in the following way. So the cohomological dimension of my field K will be the supremum of those integers n, such that there exists a torsion Galois module m, such that the Hm of Km does not vanish. Okay, so it's essentially the last degree at which the cohomology is still interesting. Afterwards, everything vanishes all the time. Well, of course, some of you might wonder why I imposed here a torsion. Well, this is the usual definition of the cohomological dimension in Galois cohomology, but you could remove it, and you get what people call the strict cohomological dimension, and it's either equal to this one or one more, so it's almost the same. All right.
Is this always finite?
No, it's not always finite. If K is the real numbers, for example, it's infinite. All right, so this is the cohomological dimension, and now, well, how does it behave? Well, let's see in the examples we had above. I can come back to my examples here. For an algebraic closed field, the cohomological dimension is 0, essentially because the absolute Galois group is trivial. For a finite field, one can prove that the cohomological dimension is always 1. In the context of the Chen-Lange-Nagata theorem, so I take a transcendence degree delta exception like this, you have always that the cohomological dimension of large K is at most the cohomological dimension of little k plus delta. And it is an equality, for example, if large K is a rational function field, if it's a little k of x1 x delta. And in the context of Greenberg's theorem, the cohomological dimension of K double parentheses T is the cohomological dimension of little k. And so when you see this, I guess you're all thinking, well, there seems to be some relation between the Slade properties and the cohomological dimension. So the naive question one might ask, is whether the field K is Ci, if and only if the cohomological dimension of K is at naive. Okay. Why do I say naive? Well, because quite quickly one can convince oneself that this is wrong. There is one implication that is not correct. From the right to left, this is wrong. And the counterexample is up there. It's given by p-adic fields. Okay. So if you look at a p-adic field, classical theory says that the cohomological dimension of the p-adic field is 2, and we've seen that it is not CI. Okay. So our question is not a good question. Still, there is the other direction, of course. So the other direction is widely open. So it's a question by Serre in the 60s. And the only known cases are the cases I equals 1. So this case is an easy exercise. And the case I equals 2, which is a very difficult theorem due to Cité. Okay, and starting from I equals 3, it's somewhat difficult. All right. So now that we have seen this, well, what can we do to go?
When is the I equals 2?
Cité is in the 80s. Okay, so now that, well, we know that one direction is wrong and the other is probably very, very, very hard, what can we do? Well, so it was Kato and Kozumaki in the 80s who had the idea to, well, maybe we can modify the CI properties in such a way that we may get at some point some just-in-time characterization of the cohomological dimension of these. Okay. And so they suggested some variants of the CI properties to try to do so. And that's what I'm going to present now. So, I think I'm getting better and better at it. Okay, so to introduce the variance of the CI properties, I need an object, which is called minimal K theory. And it's a very explicit object, so I can introduce it properly here. It's a definition. So K is my field. Okay, and I take Q in a negative integer. Well, the Qth minimal K theory group of K is defined as follows. So it's KQ of K. And so, well, first for Q equals 0, I just decided Z. Okay, and for a larger Q, well, I start from K star, the multiplicative group. I tensor it with itself Q times. Okay, and I quotient in there those pure tensors. So x1 tensor xq, such that there are two different entries that add up to 1. Okay, so this is for strictly positive. Okay, that's the definition of minimal K theory. So this definition is very explicit, but well, there are two things one has to say. Maybe if you were not used to it, you might wonder why to look at this object and so on. In fact, it's a quite natural object. So, for example, if you've already worked with Hilbert symbols over p-adic fields, so you look at quadratic forms in 3 variables over p-adic fields. Well, you have Hilbert symbols that look like a couple of numbers, A and B, and this symbol behaves in a bilinear way, and it is trivial when A and B add up to 1. So it's typically an object that lives in the K2 of K. Okay. This is one example. In fact, it appears in many other situations. For example, when you study quadratic forms in more variables and so on, typically this object plays a role, an important role. So that's one possible motivation to introduce this normal case. The second observation is that even if it's very explicit, it's not easy to compute. Okay, it's not easy to compute because, well, here you have something that's about the multiplicative group of the field, but the condition here is on the additive structure. So you have to very well understand how these interact to be able to compute this. It's not an easy task. All right, so we have this object, and to introduce Kaplan to the Mackey's conjectures, I still need one extra structure on this Milnor-K theory. So I need a norm map. So this is something that was done by Kaplan in the 80s, I think. Okay, so let's see first what happens in low degree. So if I'm at Q equals 1, popular. So what is K1 of K1 of K? K1 of K is just a multiplicative group K star, right? And so if I take L over K, a finite extension, well, I have a natural norm map from K1 of L, which is L star, to K1 of K, which is K star, and that's just the usual norm map and L over K. Determinant of the multiplication by analysis. Okay. You have this norm. You can do the same thing for Q equals 0. This is easy. So here the K0s are equal to Z. And you decide that the norm map here will be just the multiplication by the division. Okay. And the question is whether one can extend these norm maps to higher Milnor-K theory. Okay, so into a norm map that goes from KQ of L to KQ of K, of course, satisfying suits a number of compatibility relations and so on. Okay, and the answer is yes, one can define a norm map and L over K. So there exists a suitable, and by this I mean that satisfies some nice axioms, norm map in any K theory degree. And this is not obvious to construct, it's a theorem to construct. But it's possible to do.
Is it unique in some sense?
Sorry?
Is this normal map unique in some sense?
I didn't understand. That's suitable.
If it's unique.
Oh, if it's unique, yes, it is unique once you have the set of actions you want. Yes.
I'm sorry, very question. So you claim that these K theory groups have some multiplication between them, or
the transfer product.
So and the norm map should be compatible with respect to this structure.
So typically, for example, you need to have some kind of projection formula. So if you take let's say x in ki of k, y in kj of L, you want to compute the norm of x tensor y, so you want this to be x tensor the norm of y. For example, this is one of the axioms. Okay. Another axiom, you want that if you have a Tower finite extension M over L to the k, you want that the norm from M to k is computed by computing first the norm from M to L, and then the norm from L to K. Okay, so you want this concept first.
No, I was just asking about the relation between the.
So the relation between different degrees.
For different cubes.
If you want the relation between different degrees, it's this one.
So, and this essentially.
Yes. Okay, so now that I have this norm map, I'm ready to introduce the variance of the CI properties given by Katon-Kuzunoki. Okay, so definition. So this is Katon-Kuzunoki in 1986. So I take K of field, and I take two parameters, I and Q. So here I will play the same role as the I in the CI property, and Q will be the degree of Milnor-K theory we will be looking at. Okay? And the idea of Katon-Kuzunoki is to solve in the same way as the CI property. So I'm taking X inside P and K, some hypersurface of degree D with the usual inequality, D to the I is smaller or equal than N. But this time, I'm going to require something weaker than having the rational point. So what I'm going to ask is that the Qth Milnor-K theory group of K is generated by the images of the norms, so N over K of KQ of L, coming from extensions. So here L over K is a finite extension over which X has a rational point. Okay. So Milnor-K theory is generated by norms coming from extensions over which the hypersurface acquires rational points. And for simplicity, I will denote this group NQ of X over K. So what is this saying? Morally, this is telling you that, okay, if X has a rational point, well then, here you could take L equals K, and then, of course, this equality would hold, because you would have the image of the norm from K to K. In general, we're not asking that X has a rational point, we're asking this equality, and this equality is in some sense telling you that, okay, maybe X has no rational points, but it acquires rational points in sufficiently many finite extensions of K. And sufficiently many in the sense, of course, of this equality. So let me show you some examples to understand better what this means. So, examples. I think it's useful to understand the extremal examples. So, let me first take the case, let's say, I equals 0. So what does it mean for I equals 0? And Q whatever we want. Yeah, sorry. So this is a variant. I didn't give it a name. K is CIQ if I have this condition. So I equals 0. So what is C0Q? Well, if I equals 0, G to the I is more or equal than N. So I'm just saying N is at least 1. Okay, so this is almost empty as a condition. I could just take N equals 1. So I'm working in P1. If I take a hypersurface in P1, that's just a point, essentially. Okay, so point, it can be essentially any extension of K, finite extension of K. Okay, and so what I'm saying is that KQ of K, whenever I take L over K, the finite extension, well, this should be the NQ of spec of L over K. Okay, but spec of L When does it have a rational point? Over which fields? Well, those that contain L. Okay, so this is just the image of the norm map from L to K. Okay, and so I'm saying that K is C0Q. If I come there for any L over K finite, the map, the norm map, and L over K on Q's minimum K theory is surjective. So that's one of the two extremal cases. The other extremal case is when Q is equal to 0. So what happens when Q equals to 0? Well, in that case, if you think about it, here my minimum K theory is just Z. Okay? So I'm saying that Z is generated by the images of the norm sphere, but the norm is multiplication by the degree. So what I'm saying is that I have Z is generated by the degree L over K, when L over K is finite, and X has a point in R. Okay. So what am I saying? I'm saying this is also the group, if you prefer, generated by the GCD of the L over K. Okay. So what I'm saying is that, okay, X maybe does not have a rational point, but it has points in finite extensions of co-prime degrees. Okay, that's what people call the zero cycle of degree 1. So K is C I 0, example is for any X in P and K, or D, if D to the X smaller than M, well, X has the zero cycle of degree 1. If you prefer, points in extensions of co-prime degree. Okay, and so here you see that this is just a weakening of the CI property. Instead of asking the rational point, we ask that we have points in finite extensions of co-prime degrees. Yes?
So the left one, the middle one here, this is now equivalent to something about the cohomological dimension?
I'm coming to it. Yes. Yes. It's going to be that. So just before saying that, yeah. So okay, yeah, I can say that. So okay, what was the idea of Kato and Kusumaki behind these definitions? Well, what they observed is that for one of the extreme cases, this one here, they could use it to characterize the cohomological dimension. So what they observed is the following proposition. Okay, proposition. Okay, so I'm always a bit bothered. Okay, it was written in Kato and Kusumaki's paper in '86 under the condition that the block-Kato conjecture was known, but it was not known at the time. In fact, this statement is essentially equivalent to block-Kato conjecture, and this is very hard to prove by Volyvodsky. So it's essentially the block-Kato conjecture by Volyvodsky. So what we have is that the cohomological dimension of K is at most Q if and only if for any L over K finite, L is C0Q. So in some sense, the C0Q property does characterize the cohomological dimension. But of course, this is not very satisfying because if if you look at, for example, the two examples we have here, this is a not very Diophantine property. It's a very key property. What we would like, from the perspective of building a bridge between Diophantine and cohomological properties of fields, would be to have this property that characterizes cohomological dimension. Okay? And that's the question that has been ultimately raised. So the conjecture. They thought that all these CIQ properties would characterize the cohomological dimension. So more precisely, they conjectured that the cohomological dimension of K is at most I plus Q, if and only if, for any algebraic infinite,
Well, L is CIQ.
Okay. That was their conjecture. So in some way, if you make a picture, you have the cohomological dimension at most Q on one side. So this is equivalent to the fact that for any algebraic K, L is C0Q. Then you have, well, for any algebraic K, L is C1Q minus 1. For any algebraic K, L is C2Q minus 2, and so on, up to for any algebraic K, L is C Q on the lower part, 0 above. Okay, so this is the property that's here on the right. And finally, we have that K is CQ. We have all these properties, and okay, so we know that CQ implies CQ0. Okay, it's replacing rational form like 0 cycle 2 3 1. And their conjecture is that all these would be equal. And this would be much more satisfying because intuitively, if you want, here I said this is a very K-theoretic property, this is a very Diophantine property, and you have some properties that interpolate them. So the more you go to the left, the more K-theoretic you are. The more you go to the right here, the more Diophantine you are. Well, the problem is that they got it wrong. Okay, so the conjecture is wrong. So this was Mercouriet around 1990. He gave a counterexample. So he constructed the field K of cohomological dimension 2, but not C2. Okay. So Mercouriet gave a counterexample in cohomological dimension 2, and this was later improved by Colliot-Hélène and Mandor. In 2004, where they even got a counterexample in cohomological dimension 1, so K of cohomological dimension 1, but not C1Z.
Like to add to this Mercouriet thing, that it's not even C2
Yes.
upper anything.
Yes, it's not C2Q for any. Yes, that's what you want to say. Yeah, I agree. Okay, so the conjecture is wrong, and so now the question is, what can we do? Okay, now that the conjecture is wrong. And so there are mainly two remaining questions. So the first one is, okay, if one looks at these counterexamples, they are given by fields constructed by transient induction that are just enormous by adding infinitely many variables, and it's horrible fields that you never want to see in your life. So the question is whether one can prove the conjecture for reasonable fields. What do you mean by reasonable? So for example, if you start from algebraically closed fields, from finite fields, p-adic fields, number fields, you're allowed to add a finite number of variables, to take finite extensions, maybe add formal variables, this kinds of stuff. Well, this class of fields doesn't satisfy the conjecture. Okay. So that's the first question. And the second question is, well, okay, these properties CIQ do not characterize the cohomological dimension. Can one modify them further to get a characterization of the cohomological dimension? Okay. So let me.
Can I ask you something? Can we say anything about? I mean, you already said that the field extension is a little monster, right?
The field extension is a monster, yeah.
But can you say something about the degree?
of the equation.
Yeah, so you have K of cohomological degree 2, and you are claiming that there exists a finite extension that does not satisfy, say, C.
No, it's K itself that does not satisfy these properties.
Yes, but I mean, not satisfying these properties means that there exists an extension.
No, that K does not satisfy these properties. It satisfies cohomological dimension 2, but does not satisfy its properties.
Okay. This one.
Yes. K itself. You don't need to go to an extension to get the complete. In fact, if you want,
So it's
in
very wrong because
the definitions, it's just that they presented it like this, but in the definitions in their paper, in fact, the definition of CIQ is that for any finite extension L over K, for any X over L, then I'm not doing this. Okay, and I didn't want to write it like this, so that means that the price I had to pay to write the conjecture that they have to write for any other.
Are you saying the conjecture is equivalent to saying the cohomological degree is bounded by blah, if and only if, and you put K there? You don't put for all F.
No, the conjecture is for all algebraic. So the point is that the property I wrote here is not stable under finite extensions.
Yeah.
The CI property is, this one is not. So you impose that it is stable under finite extensions. Any other questions?
Like the original definition. Or
So if you want the original definition, for any algebraic was here.
Yeah.
And then you don't need to write it further.
Apologies for the earlier comment. It should be not C upper 0 lower I for any I. I think that's.
Oh yeah.
So of course, if you go Q beyond 2, then it gets to something like that. Yeah. So.
I mean this.
Yeah.
All right. So let me discuss the what one can do over reasonable fields. Over reasonable fields. So what is known? So I will discuss this, and if I have time, I will discuss the other question. But if not, well, I discussed it a little bit yesterday in the talk. So over reasonable fields, the first thing that was known was the case of p-adic and number fields. It's natural to start there from an arithmetic perspective. So there are things that are known in that case. So let me take K a p-adic or a number field. So p-adic field or a totally imaginary number field. So that K has cohomological dimension 2. So this is the reason why you impose totally imaginary. If it's not totally imaginary, the cohomological dimension is infinite, so there's nothing to say. Okay, here we are in cohomological dimension 2, so we expect 3 properties to hold in principle. So there's the C02, C11, and C20 like this. Okay. So C02 is the one that appears here. That's fine. We know it's satisfied because we know the block out conjecture. So this is fine. This is block out. The next one is the C11 property. Okay. The C11 property has been proved. So this is a theorem by Wittenberg in 2016. It's relatively recent, a long time after the conjecture. I think it's not an easy result at all. This property is true. Remains this one, so this one is the one that's in the example here. So this one is stating that if you take a projective hypersurface of degree d in Pn with d squared smaller or equal than n, it should have a 0 cycle of degree 1. Okay. And this property is still completely open. So this is open. If you manage to do this, I guess you get an announced paper without problem. This is open. It's the only case that is known only known over p-adic field if the hypersurface has prime degree. And this was in the original paper by Kaplan in 1986. Okay, so over the most usual Riemann fields, this is what is said. All right. More recently, there have been results for complete discrete valuation fields. So the kind of results you would like to have, ideally, would be results of transition type, okay? A bit like the ones that I showed you for the CI properties at the beginning of the talk. So you would like, for example, to know that if a field K satisfies some CIQ property, then Laurent series in one variable over that field satisfies some CJQ prime property. And say if you add just a variable, if you take a rational function field. So this would be the best thing to get. But it's very hard to get in this context. So what is known? Let me start with complete discrete valuation fields. It will be complete discrete valuation fields. Okay, so let me introduce the definition. So the transition property I'm going to state is not a transition property for the CIQ property, but for a stronger one. Okay? And it will allow to prove that some fields are CIQ. So this is work by, very recent work by Gambardella, who's my PhD student, and Kartas in 26, this is here. Okay, so I take K, a perfect field. And first, I define that K is stably CI if, well, every equicharacteristic same valued field, so K tilde V with divisible value group and residue field K is CI. Okay, so maybe you don't know what this chain means exactly. Doesn't matter much, it's a bit of a technical definition. If you're in equicharacteristic 0, chain means Hansel. It's the same. Okay. If you're in positive characteristic, it's a stronger assumption, but which includes Hanselian and some extra properties that I don't want to define today. Okay, so for example, typical example you should have in mind. Let's say you're in the situation where K has characteristic 0. Well, an example of such same valued field would be to take the union of the K double parentheses T to the 1 over n for n greater or equal than 1. Okay? So this field is a valued field with respect to the valuation. The valuation takes values in cube, so that's a divisible group. This is Hanselian because K double parentheses T is complete. Okay, so it's same in the case of characteristic 0, and it's equicharacteristic, the residue field is K itself. So that's a typical example. And so you're asking that these same value fields have the property CI. That's the first thing. And the second part of the definition is that we say that K is stably uniformly CIQ if, well, whenever you take K prime over K, a finite extension, there exists some subset delta of the cube Milnor K theory of K prime, such that, well, two things. The first one is that for any integer d, the subgroup generated by delta inside Milnor K theory modulo d is everything. Okay. And secondly, you ask that whenever you take an alpha in delta, there exists an algebraic extension k alpha over k, such that, well, first k alpha, so this is an infinite extension, it's not finite, it's algebraic but not finite. K alpha is stably Ci in the previous sense, and moreover, whenever you take an intermediary finite extension, so now between k alpha and k that is finite, well, you want that alpha is in the image of the group. Okay, so why is this definition made? It's made because it's a stronger assumption than being CIQ. Okay, so this is stronger than being CIQ. Essentially, to check it, I mean, it's not very difficult, but just a bit technical. But essentially, you start from your hypersurface of degree d with d to the x more or equal than n. You know that it has points in this k alpha because of the stably Ci property. Okay, and then you use the properties of the norm and so on to deduce that alpha is in the norm group, norm subgroup of Kaplan-Kozumaki for that hypersurface, and then you use the generation here to see that all the Milnor K theory is then in that group generated by norms. Okay. It's a bit technical, but essentially this is stronger than being CIQ. And the good thing is that this will be a property that is going to behave well for transition theorems. So theorem due to Gambardella and Cartas in 26. So let's take K, the perfect field, and you assume that it is a stably uniformly Ci minus 1q and Ci q minus 1. Stably uniformly Ci minus 1q and stably uniformly Ci q minus 1. Well, then, if K tilde is a complete discrete valued field equicharacteristic and with residue field K, well, you can deduce that K tilde, you have to take the perfection of it. Okay, there's a positive characteristic, you may have difficulties with an imperfect exception, is stably uniformly CIQ. Okay. So essentially this theorem is telling you that once you know that if your K satisfies some of these stably uniformly properties, a complete discrete valued field with a residue field K and then the characteristic will satisfy the next one of the CIQ properties. So it's really, the ideal would be to get this theorem for the CIQ property itself. We get it for this stronger version of the CIQ property. So what applications can we deduce from this theorem? Oh no. one can get concrete applications. Concrete applications. So for instance, so in 2017, I proved, so without using their vocabulary, but essentially that's what they put without the vocabulary, I proved that if you take the function field of a complex surface, complex variety, so actually you see the variety of dimension, let's say n, okay, well then this field C of x satisfies the Cohomological property. So this CIQ, and it's even stably uniformly. CIQ for I plus Q greater than n. That's essentially what the Cohomological property is. What the Cohomological conjecture was that this field is CIQ. In my paper, I say this field is CIQ, but if you look at the proof, it says that it's stably CIQ. Okay. They proved this a few years ago. Hence, with their theorem, you could use that if you look at C of x, the same C of x, and then you have more variables, as many as you want. And this satisfies the Cohomological conjecture. Okay, so that's one application. Another one, well, one can improve Wittenberg's proof for periodic fields to get that QP is C11 stably uniform C11. Okay, and hence from the results of there, one gets that the field QP double parentheses T1 double parentheses TM is C1 plus 1. You get this property of Cohomological for iterative power series over here. So these are two examples of applications. Okay, so it's essentially almost time. So let me just finish by mentioning the third kinds of fields people have to be looking at. So those are function fields. I've already mentioned some of them here. You know that the conjectures are true for function fields of complex varieties. What other function fields have been looked at? Well, in number theory, it's natural to look at positive characteristic Lorentz fields. So you take the function field of the curve over a finite field. Okay, and well, these fields have Cohomological dimension 2. So you expect, like for number fields, that they have C20, C11, C02. So C02 is defined by Giancarlo. Here, the C20 property is fine because we know that this field is C2. Okay, FQ is C1. That's the Chevalier-Roman theorem. And we will add one variable transform to one, then it's C2. So this is just because the field is C2. And C11 is fine, so this is something that they also in 2017. So the whole conjecture is known for positive characteristic global fields. Other case that was looked at was the case of p-adic function fields of curves. So QP of C and C is a p-adic curve. Okay. So here during cohomological dimension 3, so we expect 4 properties: C30, C21, C12, C03. And so C03 is fine, it's again Gauss-Kato. And okay, the others are in general open, but there is one result that is weaker than the conjecture, which does work. So this was myself with Lucchini-Arteche in 22. We know that this field satisfies the C22 property. So this is weaker than C21 and C12. It's weaker than these two, but it's a non-obvious property for this QPLC. Okay, so these are some specific examples. And finally, one may ask whether one can get some transition theorem for function fields. And we do not have what would be the ideal transition theorem, but we have a partial one, thanks to work again by Felipe Gambardella and this time Carichon. So the transition theorem we get is the following. Theorem, so this is Gambardella and Shaw in 2025, last year. So first you make an assumption in positive characteristics. So if the characteristic of K is P, you assume that the inseparability degree is not too large, so it's smaller or equal than P to the I minus P plus 1. Well then, if K of x1, x cubed, so the rational function field in Q variables is CIQ, then for any J greater or equal than 0, the field K of x1, x2 plus J, and J variables is Ci plus J cubed. So it's not exactly what one would like, because one would like to be able to remove the variables that are here. This means that we need at least Q variables, and Q is the degree of normal K theory at the beginning, to be able to do the implication. The ideal thing would be to be able to remove this. At least we have this theorem. And it has a very nice corollary. So when you combine this theorem with my result for positive characteristic function fields there, positive characteristic global fields, you get that the function field fq of x1, xn satisfies one of the expected properties of Kato and Kusumachi, satisfies the Cn1 property. So you manage to get a property for function fields in any number of variables in the function fields. Okay, and I've already done 5 extra minutes, so let's stop here. Thank you.